Hello everyone, I'm Pradyumna. Today I'll be presenting our work, Search for Concepts, Discovering Visual Concepts Using Direct Optimization. This work has been done in collaboration with Paul Guerrero and Niloy Mitra. Reconstructing an input signal as a composition of repeating meaningful parts has been a long-standing goal in data analysis. Let us consider the input signal shown on the screen. Decomposing it as parts, that is, different instruments and their instance parameters, which is where and how they occur in the signal, not only results in an interpretable abstraction, but also improves sample efficiency for downstream tasks. Notable classical unsupervised methods for part and parameter decomposition include principal component analysis, independent component analysis, and dictionary learning. However, all these methods have specific constraints on the part representation, like orthonormality in the case of PCA, or limitations on the kind of part instance parameters. For example, none of these methods can help with inferring explicit transformation parameters like location and rotation of the parts in the signal. These constraints make these methods specific to only one kind of composition model for representing the data. To represent the input signal as a composition of parts, there has also been work in designing priors for neural networks dubbed as object-centric representation. However, these methods are very architecture specific and do not work in low data setting. They also fail sometimes on seemingly simple data, which I'll discuss more later. Recently, methods like AlphaGo and AlphaZero have mixed direct search with amortized optimization and have shown incredible performance on many games. Inspired by these methods, in this work, we pose the question if direct optimization and search can benefit unsupervised scene decomposition. To formalize the problem statement, given a single or multiple instances of a signal, for example, like the images shown on the screen, and a composition model, for example, we can use 2D alpha blending as the composition model for images. We want to learn what the recurring elements in the data are and how and where they repeat. For example, in the case of Tetris images, we want to find the repeating primitives, their color, and the rotation in a given instance. Similarly, it would be the tree and present in the pattern example, or the strokes in the MNIST dataset. Let's jump into our method. Let us take a toy example of the pattern shown on the right. We select this because the tree concept is repeated twice and the present concept is repeated 5 times in the same instance. It is important to notice that given only this image, unlike our method, none of the previous methods can give the tree and present as the repeating concept. In step 0, we initialize our concepts with a Gaussian. This encourages the content to be in the middle of the concept. In step 1, which we call the search step, we search over the parameters of how the concepts can be composited to decrease the normalized cross correlation between the estimated deconstruction and the input image. We reformulate the search over where a concept should be placed to decrease the overall normalized cross correlation as a bunch of convolutions. Let us take a look at what this equation does visually. Given the input image, like the one shown on the screen, we start off with an empty canvas, like the buffer shown. The buffer is an estimate of the reconstruction of the input signal using the concepts. The equation takes in the buffer, or concepts, and the input image as its inputs, and outputs the normalized cross correlation value of placing the input concept at each xy location in the buffer. Then we select the xy location with the maximum correlation value and place our concept there. This would be a reconstruction of the input signal explained using just one concept. Usually, we would use multiple concepts to explain the input signal. So this reconstruction from the earlier step becomes the input to the selection of the second concept. Like what we've seen earlier, the equation takes in the buffer, our concepts, and the input image as the inputs and outputs the normalized correlation of placing the input concept at each xy location. We again select the xy location with the maximum correlation value and update our tentative reconstruction using that. We repeat this step L times to explain the input signal with L elements. After those L steps, we would have a tentative reconstruction like the image shown on the bottom right. In the second step, given the estimated reconstruction, we compute the mean square error between our reconstruction and the input signal. We update the concepts to decrease this loss value. We also perform a cloning and removing step of the concepts, which I'll discuss in later slides. To summarize our method so far, we first create a reconstruction of the input with our concepts in step 1 and improve the reconstruction by updating our concepts in step 2. Once we do step 2, we go back to step 1 and update our reconstruction based on our new concepts. And we do this for few iterations to finally learn the concepts that are repeating across an instance as well as the dataset. We can infer how they repeat using our third step. Before we take a look at the results, one thing I didn't mention that is part of second step is the cloning of the concepts. When the concepts are really similar looking, the pipeline has a local minima. We realize that cloning the concepts based on their usage helps us explain the overall dataset better. On the screen, I'm showing the clone graph of the pipeline over MNIST dataset. Let us take a closer look at this specific part of the graph. If we do not clone the concept would converge to a blurry concept that tries to explain many shapes with just one concept. However, with cloning, you can see how the concept specializes to a specific stroke shape. Now that we know the entire pipeline, let's take a look at our results. Coming back to the pattern example, let's see how our method performs at decomposing the pattern. Here, I'm showing the input image, the concepts being learned, and how they are placed, as well as the reconstruction. Notice that the method first tries to explain the input with just one concept initially. And slowly, when that is not possible, it tries to use both the concepts to explain the input signal better. You can see how concept 1 converges to the tree concept and concept 2 slowly converges to the present concept. And you can also see the overall mean square error decreasing in the bottom. In our method, we can also parameterize the shape and color of the concept separately. For Tetris dataset, we take the images as an input, we perform a search over location and rotation, and then learn the color and shape of the concept in step 2. Here, I show the results of our method on multiple dsprites binderized dataset. Neural network methods particularly struggle on this dataset because of the missing color. Notice how our method learns clear and interpretable concepts and also captures different scale variations of the concepts of the shapes in different concepts. Apart from that, our concepts and decompositions are more interpretable compared to the neural network methods. Here, we compare our method with slot attention, a state-of-the-art method in object-centric learning. Notice how slot attention decomposition doesn't handle overlap or occlusion well. Instead, it divides the object into multiple shapes in the middle. Neural network methods also seem to have a very simple failure case. When we remove a set of translations from the training dataset, the network immediately fails to converge. Here, we show our results on 3 real-world examples. Like our previous comparison, you can notice how our concepts are more interpretable than existing neural network methods. I would like to draw your attention to the experiment on the right. In this experiment, the input to our method is pages of the iRobot novel. You can notice how our method learns individual alphabets of the English language as the concepts, which is also the expected result. Our method also has a better out of distribution reconstruction numbers compared to the competition. Here, we show that our method can be trained on MNIST dataset, a dataset which contains handwritten numbers, but it can also reconstruct eMNIST dataset, a dataset which contains handwritten alphabets better than the competition. This shows that the learned concepts are transferable if we have the same data generation process, like the human writing in this case. Our method can also be extended to other modalities. For example, let us say we have multi-view renders of a 3D scene, like the silhouette images shown on the screen. Given the rendering model, we can search over the 3D parameters and learn the 3D concept just from multi-view images. Here, we show that the learned concept that are parameterized as 3D voxels that are just learned from 2D multi-view renders. The main limitation of our method is the time taken for search operation. For example, if you would like to search over possible affine transformations, this could get increasingly expensive. To alleviate this limitation, we can extend our method by learning a likelihood function for search. Such a function can be parameterized by a neural network to decrease the search space progressively. However, we leave this to the future. In conclusion, we present a general method to learn visual concepts from data without explicit supervision or learned priors. Our main idea is posing the search for visual concepts as a direct optimization, which can be solved efficiently by splitting the task into alternating dictionary finding and parameter optimizing steps. We show that our method works better than the competition on some extremely challenging datasets. We show that using direct optimization is more generalizable, misses fewer correct decompositions, and typically requires less data than methods based on amortized inference. Thank you. Check out our website for more information, and the code is available on GitHub.